Hello and welcome to Math Zone African Motives. In this video, we'll dive deep into some fundamental concepts of differentiation. Our goal is to solidify our understanding of the power rule, the product rule, and the quotient rule. By the end of this tutorial, you'll be able to confidently apply these rules to a variety of functions to find their derivatives. We'll work through 6 examples from scratch, explaining every single step. Let's begin by quickly revising the 3 main rules we'll be using. First up is the power rule. It states that if your function y is equal to x raised to the power of n, then its derivative, di/dx, is n times x raised to the power of n minus 1. This rule is used for finding the derivative of any term that is a variable raised to a constant power. Next is the product rule. If your function y is a product of 2 other functions, let's call them u and v, then its derivative is the first function u multiplied by the derivative of the second function v plus the second function v multiplied by the derivative of the first function u. You use this rule when you have 2 functions of x being multiplied together. Finally, we have the quotient rule. If your function y is a quotient of 2 functions, u and v, then its derivative is the derivative of the numerator, u times the denominator v, minus the numerator, u times the derivative of the denominator v, all divided by the denominator squared. Be very careful with the order here. The subtraction must be done correctly. We're going to solve all 6 examples from example 2.8. Here is the full question. The question asks us to determine the derivative di(x) for 6 different functions. Let's tackle them one by one. Let's start with the first example, which is a perfect use case for the power rule. Our function is y equals the cube root of x. To apply the power rule, our first step is to rewrite the function in the standard form, x raised to a power. We know that the nth root of x can be written as x to the power of 1 over n. Therefore, the cube root of x becomes x to the power of 1/3. Now our function is in the form x to the n, where n is 1/3. We can now apply the power rule. The power rule states that di(dx) equals n times x to the n minus 1. We substitute n equals 1/3 into this formula. The final step is to simplify the exponent. 1/3 minus 1 is 1/3 minus 3/3, which gives negative 2/3. So the derivative of the cube root of x is 1/3 times x to the negative 2/3. We have successfully used the power rule to differentiate the function. The key was to first convert the radical form into an exponential form. Let's move on to our second example. This one also uses the power rule, but it requires a bit of algebraic simplification first. Our function is y equals -3 divided by x to the power of -9. Again, our goal is to get this into the form of a constant multiplied by x to a power. We can use the rule of exponents that states 1 over a to the power of m is equal to a to the power of -m. Applying this, 1 over x to the -9 becomes x to the positive 9. This gives us y equals -3 times x to the power of 9. Now we have a function that we can differentiate using the power rule. Here the constant multiplier is 3, and our power n is 9. Applying the power rule, we bring the exponent 9 to the front and multiply it by our constant 3. We then subtract 1 from the exponent, making it 8. This gives us 27x to the 8th. So the derivative is -27x to the power of 8. The main takeaway here is that algebraic simplification is a crucial first step in many differentiation problems. Our third example introduces a new rule. Notice we have x cubed multiplied by cosine x. This is a product of 2 functions of x, so we must use the product rule. Let's write down our formula for di(dx) equals u prime v plus v prime u. First, we identify our 2 functions, u and v. We can set u equal to x cubed and v equal to cosine x. Next, we find the derivative of each of these, u prime and v prime. Using the power rule for u, the derivative of x cubed is 3x squared. Using the standard derivative rules, the derivative of cosine x is -sine x. Remember to memorize these standard derivatives. Now we have all the pieces we need to plug into our product rule formula. Substituting them in, we get di(dx) equals u prime times v, which is 3x squared cosine x, plus v prime times u, which is negative sine x times x cubed. Finally, we clean up the expression to get our final answer. The derivative is 3x squared cosine x minus x cubed sine x. Remember, the product rule is essential for finding the derivative of any function that can be expressed as two simpler functions multiplied together. Our fourth example presents another product, this time involving two polynomial functions. The function is y equals the quantity x squared minus 3x times the quantity 5x plus 2. Since this is a product, the product rule is the most efficient method. As before, we'll start by defining our u and v. Let's set it to be the first part, x squared minus 3x, and v to be the second part, 5x plus 2. Next, we find their derivatives, u prime and v prime. For u, we apply the power rule to each term. The derivative of x squared is 2x, and the derivative of negative 3x is negative 3. For v, the derivative of 5x is 5, and the derivative of the constant 2 is 0. So u prime is 2x minus 3, and v prime is 5. Now we substitute these into the product rule formula. I dx equals u prime times v, which is 2x 3 times 5x plus 2, plus v prime times u, which is 5 times x squared 3x. The problem isn't over yet. We need to simplify this expression by expanding the brackets and combining like terms. First, we multiply out the two binomials to get 10x squared plus 4x minus 15x minus 6. We also multiply the 5 through the second bracket to get 5x squared minus 15x. Next, we group the x squared terms, the x terms, and the constants. This gives us 15x squared minus 26x minus 6. So, the derivative of the polynomial product is 15x squared minus 26x minus 6. Alternatively, you could have expanded the original expression first and then used the power rule, but the product rule works just as well and is more generally applicable. Our fifth example is a fraction, so it's a job for the quotient rule. The function is y equals the quantity 1 minus sine x, all divided by cosine x. We need to identify our numerator u and our denominator v. Let u equal 1 minus sine x and v equal cosine x. Next, let's find their derivatives, u prime and v prime. The derivative of 1 is 0, and the derivative of negative sine x is negative cosine x. So u prime is negative cosine x. The derivative of v, which is cosine x, is negative sine x. Now we're ready to substitute these into the quotient rule formula. Di das d equals u prime v minus uv prime over v squared. Substituting our functions, we get di dx equals negative cosine squared x minus the quantity 1 minus sine x times negative sine x, all divided by cosine squared x. It's time to simplify. Be careful with the signs. The numerator becomes negative cosine squared x plus sine x minus sine squared x. Remember the fundamental trigonometric identity. Cosine squared plus sine squared equals 1. So we can rearrange the numerator to be negative of cosine squared plus sine x. This simplifies to negative 1 plus sine x. We can simplify this further by splitting the fraction. This gives us negative 1 over cosine squared x plus sine x over cosine squared x. This simplifies to negative secant squared x plus secant x tan x. You could also leave the answer as negative 1 plus sine x over cosine squared x. Both are correct. We've arrived at our final example. This is another fraction, so the quotient rule will be our main tool. Our function is y equals x plus 3 divided by x minus 2. Let's define our u and v. U is x plus 3 and v is x minus 2. Next, we find their derivatives. The derivative of u, which is x plus 3, is 1. The derivative of v, which is x minus 2, is also 1. This will make the algebra much simpler. Now we substitute into the quotient rule. Ix equals u prime minus uv prime all over v squared. Plugging in our values gives us 1 times x minus 2 minus x plus 3 times 1 all over x minus 2 squared. Let's simplify the numerator carefully. The numerator becomes x minus 2 minus x minus 3. Notice the distribution of the minus sign. The x terms cancel out, leaving us with negative 5 in the numerator. So the final derivative is negative 5 divided by the quantity x minus 2 squared. A common mistake is to forget to distribute the negative sign when simplifying the numerator, so always be on the lookout for that. Let's quickly recap what we've accomplished in this video. We started with our goal to understand and apply the power, product, and quotient rules. First, we applied the power rule, y equals nx to the n minus 1, to differentiate square and cube roots after first converting them to exponent form. Second, we used the product rule, u prime v plus v prime u, for functions that were a multiplication of two other functions. Finally, we used the quotient rule, u prime v minus v prime u over v squared, for functions that were one function divided by another. A recurring theme was the importance of algebraic simplification, both before applying the rules and after finding the derivative to present the answer in its simplest form. Mastering these three rules will give you a solid foundation for more advanced differentiation topics. Subscribe for more tutorials from Math Zone African Motives. Thank you for watching.